I am one of the AP Stats teachers at Capel High School, and I want to welcome you to this lesson. It is on transformation. And basically what we're going to be talking about today is summarized here in this screen. So let's look at the top part of the screen here. In the top part, we're talking about adding or subtracting a constant a to a random variable x. So I'm adding a constant to every observation in the distribution. So if you look at the diagram over here on the right, if this is my original distribution right here, and I add the constant a, my transform distribution will be this one right here. The mean has been moved over by a units. The first quartile has been moved over by a units. The third quartile has been moved over by 8 units. Every location has been moved over by 8 units. But the spread does not change. So here I have the spread of the distribution of x plus a is equal to the spread, the standard deviation of x. And the variance of x plus a is equal to the variance of x. And as you can see also, the shape does not change. Both of these have the same shape. Now things are slightly different if we multiply or divide a random variable x by a constant b. So let's just look at this diagram that we have here in the bottom, and you can see that if my original distribution is this middle one, and I multiply it by a constant b that's less than 1, then all the values are going to become a little bit closer to 0, and be, half the values that they were before. So that'll make the distribution taller and skinnier. If I multiply by a constant b that is greater than 0, then my distribution is going to flatten out and become wider. So here's what's happening mathematically. If I take every observation in the distribution and multiply it by b, that means the mean of the constant also increases by b. So the mean of the distribution of bx is equal to the b times the mean of x, or the expected value of x. But what happens to the spread? Well, the spread of the new transformed variable bx is equal to the absolute value of b times the standard deviation of x. Why absolute value of b? Well, because b might be a negative number, and we've got to make sure that our standard deviations are all positive. With regard to variance, it's slightly more complicated. The variance of the new distribution bx is equal to b squared times the variance of x. So I'm going to take a second here and show you how this is applied, and we're going to go over to the worksheets for today. Here we have some data on Brookhaven Community College. Brookhaven Community College considers a student to be a full-time student if he or she is taking between 12 and 18 units. The number of units x, that's my random variable, that a randomly selected Brookhaven Community College full-time student is taking has this distribution. So you can see that a quarter of the students here had 12 credit hours. 1/10 of the students had 13 credit hours. So let's just review a little bit from last class period. We want to calculate and interpret the mean and standard deviation. Well, this right here is that right there is a symbol for expected value of x, and it is equal to the mean of x. And what I'm basically doing is I'm taking each observation x, multiplying by its probability, and then adding all of those together. I don't have to write all of those out. I can just write 2 of them. In this case, I've chosen to write the first and the last. And the sum total is 14.65 units. Make sure you have your units at the end. And how do we interpret that? If we randomly select many full-time students at Brookhaven Community College, the average number of units they would be taking is about 14.65 units. Now let's calculate the variance, or standard deviation. Now there's 2 ways of doing it. We can calculate the variance first and then take the square root of that number. Or we could go directly to our standard deviation formula. Now, I'm going to just explain briefly the standard deviation formula. So what I have here, we just calculated our mean to be 14.65. So I'm going to take each observation, 12 minus the mean, I'm going to square it, times the probability. Then I'm going to add 13 minus the mean of 14.65, square it, and multiply it by its probability. And dot, 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 and I'll get to my final term here. 18 minus my mean of 1465, square it times 0.15. So that'll give me my variance. And if I take the square root, then I'll have my standard deviation. Now, if you want to be a little bit more brief in your presentation, you can write it all in one step. So here I have each of the things that I'm adding. I've only shown 2 of them, but I have this plus dot, 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 plus in between, so the reader knows that I know how to apply the formula. It's just a lot of writing. And I get an answer of 2.056. Okay, I want to interpret this first, and then I'm going to go back and show you how to do this on the calculator. Interpretation: if we randomly select many full-time students at Brookhaven Community College, the number of units taken typically varies by about 2.056 from the mean of 14.65. All of these underlined words are important and part of the grading rubric. You have to say that the samples were randomly taken and that you're taking many samples. Then you describe your variable, the number of units taken. And here's your magic words for standard deviation. Typically varies, number of units typically varies by about, and here's my standard deviation that I calculated. What does it vary from? Well, it varies from the mean, and then I put the value for the mean. Now, I have a line here, and I want to just emphasize this. The line right above, this is my calculation of standard deviation. That line is considered the minimal acceptable work for standard deviation, and you always have to show your work. But oftentimes, we'll just plug the numbers into the calculator to come up with our answer. We have to write this out to show our work, but the answer will come from the calculator. We're not going to punch in all these numbers. So let me just take a second here and show you how we get all those numbers into our calculator. Here's my data, and I take out my calculator. It looks kind of like this. I know it's a bit small on your screen maybe. I put the top row of numbers, 12, 13, 14, in list 1. I put the probabilities, 0.25, 0.10, in list 2. Now I want to calculate the mean and standard deviation, but before I press 1 var, press F1 for 1 var, I want to check to see how it's setting. This is what happens a lot of times if your calculator's been reset. We have the frequency set at 1. We have the data, our x values, our random variables in list 1, but we want to set the frequency equal to the probability that we have in list 2. So I'm going to hit F2, set it at 2, and now I have the frequencies coming from list 2. That's what I want. So I'm going to step down here, press my execute button, and now I can press F1 for my 1 var, and I can see, yeah, there's my x bar, my mean of 14.65, and my standard deviation of 2.056, and that should match pretty nicely with my x bar of 14.65 and my standard deviation of 2.56. So that's how you should do it on the calculator. I'm going to come back here and we're going to continue forward. Now, this is the part where we get to the transformations. At Brookhaven College, the tuition for full-time students is $50 per unit. So if T is the tuition, then my equation is just T equals 50 times X. I take every X and I'm going to multiply it by $50, and that's going to give me my tuition. So I could do it the hard way, like this, and create a new table where instead of having, 12 credit hours right here with number of units at X, I'm going to have the tuition, and that's just going to be 12 times 50 and 13 times 50. And I could go ahead and calculate the mean just like I did before, and you'd see that the mean is now 732. But there's an easier way of doing this, and that is, since I'm just multiplying every number by 50 to get my tuition, by properties of mean, I know that the expected value or mean of T is just 50 times the expected value of X. So I can take my mean of X, multiply it by 50, and I get 732 $8.50. So this is a pretty snazzy, pretty easy way of calculating the mean. If you know the mean of x, you just multiply that by $50 to get the mean of t. Similarly with standard deviation, I could beat it out with this long formula right here, and I could punch all those numbers in my calculator. But I could just instead rely on the principles of standard deviation, because what I told you before is that the standard deviation of t is just going to be, which is the standard deviation of 50x, is just 50 times the standard deviation of x. So let's see if that is true. If I take 50 times my standard deviation of x, I get 102.80, which is exactly the number that I get right here when I do it the long way. So that's why we say when you're multiplying or dividing by a random variable x, all I have to do is take the old mean and multiply it by my constant b, and that'll give me the mean of the new variable. Similarly, if I know the standard deviation for x, my standard deviation for my transform variable is just the absolute value of my constant times the standard deviation of x. That's how you handle multiplying or dividing by a constant. Now let's talk about what happens if we add a constant. Well, we should expect this is even easier. So in addition to tuition, each full-time student at Brookhaven is assessed a student fee of $100. So their total cost, if C is the overall cost, their total cost is just their tuition cost plus $100. Now I could beat this down by again putting the new values for each of my costs, calculating, if they had 12 credit hours, what would be their tuition, and then add $100, and that'll give me their total cost. And I could calculate that the hard way, just like this. But when I added a constant 100, all I'm doing is taking all the observations from my previous distribution of t's and shifting them over 100 units. So it should be no surprise then that the expected value of C is just the expected value of the tuition plus $100. Well, what was our expected value of tuition? That was $732. I add my $100 and I get a mean cost of $832, which is exactly what I would have gotten had I done it the long way. How about standard deviation? Now, when I add a constant, the standard deviation doesn't change. Let's see if that holds true in our example right here. So I'm adding a constant. Now I want to calculate the standard deviation. One way of doing it is the long way, like that, and I get the same standard deviation as I had before. Or I could just rely on my formula. I know that the standard deviation of t plus 100, my new variable t plus 100, is equal to the standard deviation of t. So my standard deviation for my cost is equal to the standard deviation for my tuition, which is equal to 102.8. Standard deviation stays the same when you add a constant. Okay? Now, and here's what I said right here. Now, if we combine these, then we have what is called a linear transformation. A linear transformation is a transformation of a random variable that involves adding a constant a, multiplying by a constant b, or both. So if I have a random variable x, and I multiply it first by every observation first by b, and then I add an a to every observation, I'm going to get this new variable y. What is the mean of y? It's just a plus b times the mean of x. I substitute the mean of x into my transformation equation up here. Okay, and the same holds for median and every measure of location. If I have the first quartile of x, I can plug that into this equation, and it'll give me the first quartile of y. Now, with regard to linear transformations for standard deviation, that's slightly different. When we have a transformation and we're calculating the standard deviation, we don't have to worry about that a. Adding that constant a doesn't do anything to the standard deviation. So all I'm going to do is my standard deviation of y is equal to my absolute value of b times the standard deviation of x. Why make it an absolute value of b? Because just in case b is negative, we always have to have a positive standard deviation. Okay, and again, if we're dealing with variances, that means we just have to square everything. So the variance of y is equal to b squared times the variance of x. And, scaling a test. Yeah, this is a good problem too. Let me talk about this for a second. In a large introductory stats class, the distribution of x is defined as the raw scores on a test. We know that it is normally distributed with a mean of 17.2 and a standard deviation of 3.8. But the professor decides to scale them differently. He wants them to take each value and multiply it by the raw score by 4 and add 10. So my new transformed equation is this. If x is my original distribution, then I'm going to multiply it by 4 and add 10, and that'll give me my new transformed distribution. And we're told that x is distributed initially 17.2 as a mean, 3.8 as standard deviation. How do I find the mean of y? All I'm going to do is take the mean of x and put it into my transformation equation. So 4 times 17.2 plus 10 gives me 78.8. And all you have to do here is just cite that this is true by properties of expected value. How about standard deviation? Well, standard deviation is not affected by this 10. It's only affected by the 4. So all I have to do is to get the standard deviation of y, I'm going to take 4 times the standard deviation of x, and I get 15.2. And that's true by the properties of standard deviation. So if the original distribution is normal, then my transformed equation is also normal, but now it has a mean of 78.8 and a standard deviation of 15.2. That's all I'm going to cover right now. Thank you for listening.